The construction of the coastal viaduct in Réunion is truly an exceptional project that showcases the innovative methods and materials used to create a secure and durable traffic access between Saint-Denis and La Possession. One of the key aspects of the construction process is the geotechnical reconnaissance campaign conducted by the platform led by Mayor Adrian. The deep-sea surveys carried out up to 25 meters deep have helped to determine the quality of the soil and ensure a stable foundation for the viaduct supports. This step is crucial in guaranteeing the long-term durability of the structure while protecting marine life and the delicate ecosystem. The construction process itself heavily relies on prefabrication, with over 95% of the structure being built on land. The two prefabrication factories dedicated to this project, located behind the East Port, allow for better quality control and a more controlled environment during construction. The first factory focuses on producing the tabling, consisting of 1386 vissoirs, while the second one manufactures the piles in two sections, the lower part with the base and the upper part with the chevetre. This approach ensures that the viaduct's components are constructed to high standards before they are assembled at the construction site. The transportation of the massive pile parts, some weighing up to 4,500 tons, is made possible by a custom-built mega barge. This impressive barge, measuring 107 meters in length and 44 meters in width, equivalent to the size of a football field, can withstand cyclones and tropical storms. It ensures the safe transportation and placement of the viaduct's components, mitigating potential risks during the construction process. The assembly of the viaduct's tabling is a significant undertaking, with vissoirs transported by night in exceptional convoys to be assembled on both sides of the sea piles. As the construction progresses, various elements such as guardrails, barriers, waterproofing, and the first layer of asphalt are added to the viaduct, completing the structure and making it ready for its future use. One remarkable aspect of this project is the careful consideration of the environment. The 6 piles located at the Point du Gouffre are designed with structures to promote the reconstitution of marine life. These measures encourage the hatching of rich fauna and the growth of fry in a protected environment, contributing to the preservation of the marine ecosystem in the area. Visualizing the future road through a 3D projection allows us to see the grandeur and complexity of the coastal viaduct. The viaduct gracefully spans over 5 kilometers, its majestic structure rising 20 to 30 meters above sea level. As we follow the road on the viaduct, we can appreciate the breathtaking coastal views on one side and the vast expanse of the Indian Ocean on the other. The 50 supports, 48 of them located in the sea, form a symphony of engineering marvels that blend seamlessly with the natural surroundings. The Nissi-Euphrates Bridge, also known as the Nissi Bridge, Turkish, Nissi Köprüsü, is a remarkable cable-stayed bridge located in southeastern Turkey. It spans the vast Ataturk Reservoir on the Euphrates River, marking the provincial border between Adıyaman and Şanlıurfa. Before the construction of the new bridge, the original one was submerged during the creation of the reservoir in 1992, which led to the disconnection of the highway link between Adıyaman and Diyarbakır. To bypass the detour and restore the crucial transportation link, the Nissi Bridge project was initiated. Construction of the Nissi Bridge began on January 26, 2012, and the bridge was officially opened on May 21, 2015, by President Recep Tayyip Erdoğan. The construction was led by Gülsen Construction Company, and the total cost of the project was estimated to be $100 million. This impressive engineering feat involved overcoming several challenges, with seismic hazards being a major concern. The bridge's location in the area of the East Anatolian Fault, one of Turkey's most seismically active regions, demanded meticulous planning and design to ensure its safety and stability. One of the primary challenges in building the Nissi Bridge was the complexity and cost associated with positioning the bridge pier within the reservoir of the Ataturk Dam. To address this, the bridge was designed with a single main central span of 400 meters, crossing the reservoir with 2 pylons rising to a height of 96.8 meters each. The pylons represent approximately 1/4 of the main span's length and serve as vital support for the cable-stayed orthotropic bridge. The Nissi Bridge boasts impressive technical specifications, making it an exemplary project in Turkey's construction sector. It stretches 610 meters in length and is 24.50 meters wide, accommodating 2 lanes of traffic in each direction. The bridge includes a 1.5-meter walkway and a 1.5-meter emergency lane on either side, in addition to the 3.5-meter traffic lanes. With these features, the Nissi Bridge facilitates smoother and more efficient travel between the cities of Adıyaman and Diyarbakir, considerably reducing the travel time and enhancing connectivity in the region. Moreover, it has significantly contributed to the economic and social life of the area by providing improved access between the 2 sides of the Euphrates River. The bridge's name, Nissi, pays homage to the ancient town of Nissi, which was once situated in the surrounding area. Its completion and functionality have been crucial for the people in the region, allowing them to enjoy increased accessibility and better transportation options. The Nissi Bridge stands as a testament to human ingenuity and engineering prowess, overcoming challenges posed by nature and geography to create a vital link for southeastern Anatolia. As Turkey's 3rd largest bridge, it represents a symbol of progress and development in the country's infrastructure landscape. The Nissi Bridge was meticulously designed and constructed to meet the region's infrastructure needs, while taking into account the challenging terrain and seismic activity prevalent in the area. The project involved various stages of development, starting from conceptualization and tender design to engineering and consulting services. The ICE, Institution of Civil Engineers and Consulting Services, played a crucial role in ensuring the bridge's safety, structural integrity, and adherence to engineering standards. In terms of its physical attributes, the Nissi Bridge is an architectural marvel. It spans a total length of 610 meters, with the central span reaching an impressive 400 meters in length, making it the bridge's longest section. The span arrangement is denoted as 105.0 plus 400.0 plus 105.0, indicating the distribution of spans on the bridge. The pylon height stands at 96.8 meters, adding to the bridge's grandeur and providing essential support for the cable-stayed structure. The bridge has a width of 23.3 meters, allowing sufficient space for 4 lanes of traffic, with 2 lanes in each direction, identified as D360. This width accommodates the smooth flow of vehicles while considering safety aspects. The design and construction of the Nissi Bridge involve the use of different materials and foundation types. The main span of the bridge features a steel orthotropic box girder structure, which is a type of bridge design that uses steel plates welded together to form the main load-carrying element. This design offers high strength-to-weight ratio, making it suitable for long-span structures like the Nissi Bridge. On the other hand, the side spans are constructed using pre-stressed concrete boxes, ensuring durability and structural stability. The bridge's foundation is designed as shallow on massive concrete blocks, allowing for a stable base on the reservoir's bed. The balanced cantilever method was employed during the construction process, enabling safe and efficient construction of the bridge's main span without the need for temporary supports. The Nissi Bridge is classified as a cable-stayed bridge, featuring a unique and visually striking cable system that supports the main span from tall pylons. The bridge deck material, as mentioned earlier, is an orthotropic steel deck, chosen for its strength and reliability. This material can withstand heavy loads and is well suited for large bridges like the Nissi Euphrates Bridge. The segment of the Nissi Bridge weighs an impressive 250 tons and is a crucial component of the bridge's construction. It is situated in the area known as Duba, within the overall structure known as Kiris. The construction of the main span of the Nissi Bridge employed the innovative and widely used engineering method known as the balanced cantilever method. The balanced cantilever method is a technique used for constructing long-span bridges, and it played a pivotal role in building the main span of the Nissi Bridge. This method involves starting the construction from both pylons, with segments of the bridge deck being extended and gradually joined until they meet in the middle to form the main span. The segments are constructed in a balanced manner to ensure that the forces and loads on each side of the bridge remain equal during construction. Temporary supports were employed during the construction process to provide stability and maintain the balance of the structure until the segments were connected, forming the main span. As each segment was added, engineers and construction workers meticulously monitored the process to ensure that the bridge maintained its structural integrity and alignment. The balanced cantilever method was chosen for the Nissi Bridge due to its effectiveness in constructing long spans without the need for extensive temporary supports in the water, which would have been challenging and costly given the bridge's location on the Ataturk Reservoir. This method allowed for efficient construction, reduced construction time, and minimized disruption to the water traffic during the building process. By utilizing the balanced cantilever method, the Nissi Bridge's main span was successfully constructed, achieving a length of 400 meters and connecting the two pylons on either side of the Ataturk Reservoir. This engineering feat not only showcased the technical prowess of the project's design and construction teams, but also ensured the safety and stability of the bridge. The segment weighing 250 tons is a critical element of the Nissi-Euphrates Bridge, located at a specific location known as Kiris, referred to as Dub. This segment played a crucial role in the overall construction of the bridge, contributing to its structural integrity and load-bearing capacity. In the context of bridge construction, a segment refers to a discrete part of the bridge deck or structure that is prefabricated or constructed separately and then integrated into the bridge during the assembly process. The segment at Kiris, weighing 250 tons, was likely a substantial section of the bridge deck that required precision engineering and careful handling during both fabrication and installation. The year 2014 marked a significant milestone in the construction timeline of the Nissi Bridge, with construction activities and progress at Kiris being particularly noteworthy. At an elevation of 532 meters above sea level, the bridge's location showcases the engineering challenges and complexities faced during its construction. Building a large-scale infrastructure project like the Nissi Bridge at such an elevation required specialized construction techniques and careful consideration of environmental factors, such as weather conditions and access to resources. The Kiris segment was likely installed using advanced engineering methods, such as the balanced cantilever method or other appropriate construction techniques, to ensure its seamless integration into the overall bridge structure. It is essential to note that each segment's accurate placement and alignment are crucial to maintaining the bridge's overall stability and safety. Given the substantial weight of 250 tons, the transportation and installation of the Kiris segment would have required heavy-duty cranes and specialized equipment. The bridge's construction team would have meticulously planned and executed the installation process to ensure the segment's safe and precise placement. The Nissi-Euphrates Bridge is an impressive highway bridge located in southeastern Turkey, specifically on the Adıyaman-Diyarbakır Highway. Completed in 2015, the bridge serves as a vital transportation link between the cities of Adıyaman and Diyarbakır, crossing the Ataturk Reservoir on the Euphrates River. The project falls under the category of a highway bridge, designed to accommodate high volumes of traffic and reduce travel time between the two cities significantly. The Hardanger Bridge, also known as Hardanger Brua, stands as an impressive feat of engineering and a testament to Norway's commitment to modern infrastructure. Spanning across the Eidfjorden branch of the majestic Hardangerfjorden in Vestland County, Norway, this suspension bridge has become a vital connection between the municipalities of Ullensvang and Ulvik. Prior to its construction, travelers had to rely on a ferry service between Bruvik and Brimnes, which considerably lengthened the driving time between Oslo and Bergen. However, with the advent of the Hardanger Bridge, the journey became faster and more convenient. The project received approval from the Norwegian Parliament on February 28, 2006. And construction work commenced on February 26, 2009, under the guidance of the Norwegian Public Roads Administration. The construction was skillfully executed by Mount Hojgaard, and the entire project had a budget of 2.3 billion kr, 290 million euros, Interestingly, more than half of this funding was to be generated from tolls and saved ferry subsidies, making it a partly self-sustaining endeavor. The Hardanger Bridge is an architectural marvel, measuring an impressive 1,380 meters, 4,530 feet in length, with the main span stretching over 1,310 meters, 4,300 feet. The bridge deck reaches a maximum height of 55 meters, 180 feet, and the iconic towers soar to an impressive 200 meters, 660 feet, above sea level. With 2 driving lanes allowing a speed limit of 80 kilometers per hour, 50 miles per hour, the bridge facilitates the smooth flow of vehicular traffic. Additionally, to ensure the safety of pedestrians and cyclists, there is a separate lane dedicated to their use. One of the notable advantages of the Hardanger Bridge is the significant reduction in travel time between Oslo and Bergen, which are 2 of Norway's major cities. This has not only benefited commuters and travelers, but has also contributed to the economic development of the region. The construction of the bridge also presented an opportunity to re-evaluate the main connection between East and West Norway. The Norwegian Public Roads Administration is reportedly exploring the possibility of a different route that could further enhance transportation infrastructure. The breathtaking main span of the Hardanger Bridge is not only one of the longest suspension bridge spans in the world, but also holds the distinction of being the longest tunnel-to-tunnel suspension bridge. On the southern end of the bridge, motorists enter the BU Tunnel, a 1.2-kilometer, 0.75 miles tunnel passing under the village of BU. On the northern side, the journey continues through the 7.5-kilometer, 4.7 miles, Viaduct Tunnel, which includes a 500-meter, 1,600 feet long segment leading to a roundabout situated inside the tunnel. From there, travelers have the option to proceed through a 500-meter, 1,600 feet long tunnel to Ulvik or take the longer 7-kilometer, 4.3 miles tunnel to Greenfield. The installation of the force play saddles proved to be the next significant challenge for the bridge engineers working on the Hardanger Bridge project. These saddles, much like the pylon saddles, are constructed using solid steel, ensuring durability and strength to withstand the forces acting on them. Each individual force play saddle impressively weighs a substantial 23 tons, showcasing the magnitude of engineering precision required for their successful placement. The installation process demanded millimeter-level accuracy to ensure the proper functioning and structural integrity of the bridge. Any deviations or errors during this critical phase could have severe implications on the bridge's overall performance and safety. To facilitate the installation of the force play saddles, both pylons had to be pulled back half a meter toward the anchorage before the steelwork across the fjords could commence. This adjustment was necessary to create the necessary space and alignment for the force play saddles to be securely positioned at the very front of the splay chambers. The saddles had to be anchored in a manner that would distribute the immense forces evenly and effectively throughout the bridge's structure. Once the installation of all the steelwork was completed across the fjords, the pylons would be carefully brought back to their original vertical positions. This intricate process would ensure that the bridge achieved its intended design and functionality, allowing it to bear the anticipated loads and pressures over its lifetime. The installation of the catwalk was a crucial and exciting phase in the construction of the Hardanger Bridge. To transport workers across this vast expanse, a purpose-built man basket was utilized. This basket was specially designed to safely carry personnel and equipment to various locations along the bridge. The sheer height and scale of the bridge project made transportation logistics a significant challenge, and the man basket provided a reliable solution for moving workers to their designated work areas with ease and safety. The completion of the catwalk on the 5th of September 2011 marked an important milestone for all those involved in the project. It was a moment of pride and accomplishment, as the workers could now traverse the entire length of the bridge, experiencing the breathtaking views and majestic surroundings of the fjord as they went about their tasks. Beyond its practical purpose, the catwalk also served as a symbolic connection between the engineers and workers and the monumental structure they had created. For the first time, the bridge was accessible to more than just construction personnel. On this special occasion, the project team and other guests were given the unique opportunity to walk across the bridge, marveling at its grandeur and appreciating the magnitude of their collective efforts. The catwalk not only facilitated the installation work during the final stages of construction, but also played a vital role in conducting inspections, maintenance, and any necessary repairs after the bridge's completion. Its presence ensured that the bridge would remain safe and functional for the years to come. The cable system of the Hardanger Bridge is a marvel of engineering precision and strength. Each cable wire is meticulously fixed to the strand shoe, located in the anchorage block at the bottom of the splay chamber on each side of the fjord. These cables play a vital role in supporting the bridge's structure and distributing the load from the bridge deck to the pylons. The cable wires used in the Hardanger Bridge are remarkably robust, with each wire boasting a diameter of 5.3 millimeters. To form a cable, 19 strands are brought together, and each of these strands consists of an astonishing 528 individual wires. The process of forming the cable involves compacting the wires into their circular shape, which is primarily achieved through a machine operation. However, the work team also contributes with some manual input to ensure the cables are perfectly shaped and aligned. Once the cables are in their final shape, 44 cable clamps are attached to them. Among these, 40 clamps are installed on the side spans, securing the cables firmly in place. The cable clamps are crucial in maintaining the integrity of the cable system and ensuring that it can effectively support the bridge's structure and load. With the cables now securely in place, the next step is to fit them with hanger clamps. The hangers are an essential component of the suspension bridge design as they connect the bridge deck to the suspension cables, allowing the deck to be suspended in mid-air. For the Hardanger Bridge, a total of 130 hangers are required. The current Greenfield Bridge, officially known as the Beechwood Boulevard, Greenfield, Bridge 2, stands as a testament to modern engineering excellence and community resilience. Open to traffic on October 15, 2017, the new bridge replaced the aging second Greenfield Bridge, fulfilling the vital role of connecting the neighborhoods of Greenfield and Squirrel Hill, specifically Shenley Park, over the valley of 4 Mile Run, while also spanning the bustling Parkway East, I-376, that runs along the valley floor. Designed and engineered by HDR Inc., the Beechwood Boulevard Bridge 2 was constructed with meticulous attention to detail and architectural homage to the original structure that once graced this significant crossing. With a construction cost of $17.5 million, this investment showcased Pittsburgh's dedication to providing its residents with a durable and modern transportation link. One of the most striking aspects of the new Greenfield Bridge is its aesthetic resemblance to the original wooden bridge that once stood at this location. The bridge's design echoes the classic arch shape, evoking a sense of nostalgia while embodying the city's historical roots. Many of the stone ornaments salvaged from the original bridge's wreckage were lovingly restored and integrated into the new structure, further solidifying the bridge's connection to the city's past. Beyond its visual allure, the current bridge boasts enhanced functionality to cater to modern transportation needs. Wider lanes and sidewalks ensure smoother vehicular and pedestrian traffic flow, enhancing safety and convenience for users. Recognizing the growing popularity of cycling, the bridge was thoughtfully equipped with a dedicated bicycle path, encouraging a greener and more sustainable mode of travel. The Greenfield Bridge 2 is constructed primarily of steel, known for its strength and durability, making it a reliable and long-lasting asset to the city. In a nod to the community it serves, the steel elements of the bridge are painted green, reflecting Greenfield's identity and symbolizing the bridge's connection to its neighborhood. The new Greenfield Bridge's length spans an impressive 462 feet, 141 meters, with its longest span stretching an awe-inspiring 287 feet, 87 meters. This monumental feat of engineering stands as a testament to human ingenuity, seamlessly blending form and function to create a bridge that not only facilitates transportation, but also adds to the city's architectural splendor. The project's successful completion was the result of collaboration between engineers, architects, construction crews, and the community. It reflects Pittsburgh's commitment to preserving its historical landmarks while embracing innovation to meet the demands of a growing city. The Greenfield Bridge 2 represents not just a physical structure, but also a testament to the power of perseverance and the importance of investing in a better, more connected future. With its picturesque location, the Greenfield Bridge 2 stands as a symbol of unity, connecting communities, and fostering a sense of pride among the residents of Greenfield and Squirrel Hill. As Pittsburgh's landscape continues to evolve, this magnificent bridge will undoubtedly continue to play a pivotal role in the city's history, leaving a lasting legacy for generations to come. The Greenfield Bridge, officially known as the Beechwood Boulevard Greenfield Bridge 2, is a historic steel arch bridge located in Pittsburgh, Pennsylvania, United States. Spanning the picturesque valley known as 4 Mile Run, the bridge serves as a vital link, connecting the vibrant neighborhoods of Greenfield and Squirrel Hill, specifically Shenley Park. Its strategic location also allows it to gracefully span the bustling Parkway East, I-376 that runs along the valley floor. The history of this crossing dates back to the late 19th century when the first bridge was constructed in 1891. The original structure, a wooden deck truss bridge, was initially referred to as the Forward Avenue Bridge and later became known as the Beechwood Boulevard Bridge when it became the southern terminus of the newly built Beechwood Boulevard in 1898. Despite its significance, the wooden bridge faced serious structural issues, necessitating multiple repairs over the years. Tragically, it eventually succumbed to its challenges and collapsed on June 18, 1921. Fortunately, at the time of the collapse, the bridge had been closed to vehicular traffic, sparing lives, but leaving the community without a vital transportation link. In response to the loss, a new concrete arch bridge was designed and constructed between 1921 and 1923. This sturdy structure, spanning 466 feet, 142 meters in total length, featured a 274-foot, 84 meters main span and was designed by Chief Engineer Charles M. Reppert and architect Stanley L. Rausch. It was an architectural marvel of its time, adorned with decorative elements such as ornamental entrance pylons, light standards, and urns, adding an artistic touch to its functional design. The city of Pittsburgh also constructed 6 other similar bridges during the 1910s and 1920s, but only the Larimer Avenue Bridge remains standing today. Finally, after decades of wear and tear, the decision was made to replace the second Greenfield Bridge. On December 28, 2015, the old bridge was imploded, marking the end of an era and clearing the way for a new and improved structure. The construction of the third bridge commenced, and on October 15, 2017, the Beechwood Boulevard Greenfield Bridge 2 opened to the public. The new bridge, designed and engineered by HDR Inc., beautifully pays homage to the original structure by mimicking its appearance and incorporating many restored stone ornaments. However, it is equipped with modern features to meet contemporary transportation needs. The third bridge, made of steel, spans 462 feet, 141 meters, and offers wider lanes, sidewalks, and a dedicated bicycle path. Its green-painted steel elements symbolize the bridge's strong connection to the community of Greenfield, as well as its commitment to a greener and sustainable future. The first Greenfield Bridge, an iconic wooden deck truss bridge, holds a significant place in the history of Pittsburgh, Pennsylvania. Constructed in 1891, it provided a vital crossing over the valley known as 4 Mile Run, connecting the neighborhoods of Greenfield and Squirrel Hill, specifically Shenley Park. Initially known as the Forward Avenue Bridge due to its location on Forward Avenue, it later became an integral part of the newly established Beechwood Boulevard in 1898, serving as the boulevard's southern terminus. The original Greenfield Bridge boasted impressive dimensions, stretching approximately 378 feet, 115 meters in length, and 30 feet, 9.1 meters in width. Its commanding presence not only facilitated transportation, but also added to the aesthetic appeal of the surrounding landscape. Beechwood Boulevard, a 9-mile, 14-kilometer carriageway, created a scenic route from Shenley Park. meandering north to Highland Park, enhancing the connectivity between these regions. However, over the years, the bridge encountered serious structural issues that demanded frequent repairs. The wear and tear inflicted by time and weather took a toll on the aging wooden structure. Despite the repair efforts, the bridge's condition continued to deteriorate, and it faced increasing challenges to sustain the weight and pressure of vehicular traffic. The inevitable disaster struck on June 18, 1921. The Greenfield Bridge, already closed to vehicular traffic for over a year due to its precarious state, tragically collapsed. The collapse occurred at around 2:40 on a Saturday afternoon, a time when the bridge was still frequented by pedestrians. By a stroke of luck, no one was injured in the catastrophe, but 5 individuals who had either just crossed the bridge or were about to do so narrowly escaped harm. The collapse of the original Greenfield Bridge left the community in shock and in need of an urgent solution to restore this vital link between the neighborhoods. Plans were quickly set in motion to replace the fallen wooden bridge with a new and sturdier structure. Despite its brief existence, the first Greenfield Bridge left an indelible mark on the city's history. It symbolized the growth and development of Pittsburgh in the late 19th century, connecting communities and opening new avenues for transportation. Its untimely collapse marked a turning point, leading to the construction of the second Greenfield Bridge, a concrete arch bridge, which in turn would undergo its own journey through the annals of time before being replaced by the third and current steel arch bridge. The construction of the second Greenfield Bridge, a remarkable open-spandrel concrete arch bridge, marked a new chapter in Pittsburgh's infrastructure history. In response to the collapse of the original wooden bridge in 1921, plans were swiftly put into action to design and build a more resilient and long-lasting replacement. Work on the new bridge commenced in 1921 and progressed over the course of 2 years, with completion achieved by December 1922. However, some finishing touches, particularly the filling in of certain approaches, extended the timeline, and the bridge was fully ready for public use shortly thereafter. The total cost of this ambitious project amounted to $370,000, a substantial investment that reflected the city's commitment to creating a durable and aesthetically appealing structure. Officially known as the Beechwood Boulevard Bridge, the second Greenfield Bridge was commonly referred to as the Greenfield Bridge, owing to its crucial location connecting the Greenfield and Squirrel Hill neighborhoods. With a total length of 466 feet, 142 meters, the bridge's main span extended an impressive 274 feet, 84 meters, standing as a testament to engineering ingenuity of the time. The bridge's design was an architectural marvel, masterminded by Chief Engineer Charles M. Reppert and architect Stanley L. Rausch. It featured a unique open spandrel arch design, which not only provided strength and stability, but also lent an elegant and timeless appeal to the structure. To add a touch of grandeur, the bridge incorporated decorative elements, including ornamental entrance pylons, light standards, and urns, further enhancing its visual allure. The Greenfield Bridge was part of a larger endeavor by the city of Pittsburgh, which constructed 6 similar bridges during the 1910s and 1920s. While these bridges were equally impressive in their design and functionality, only the Larimer Avenue Bridge stands as a survivor, attesting to the significance and legacy of the second Greenfield Bridge. Over the years, the Greenfield Bridge became an iconic symbol of Pittsburgh's engineering prowess and urban development. However, like its predecessor, it faced challenges with wear and tear, necessitating periodic maintenance and repairs. By the 1970s, the bridge had begun to show signs of decay, with pieces of concrete falling from its structure, leading to temporary closures and safety measures. Despite efforts to preserve its original ornamental features, the bridge underwent changes during a rehabilitation project in 1980-81. When most of the decorative elements on the bridge deck were removed. Unfortunately, incidents of falling concrete persisted in subsequent years, prompting the city to install safety netting to protect the parkway east below.